fantastic to see you all still here. We are surprisingly on time for our final presentation of the day. So we've heard a lot about Ethereum 2.0, Xiaowei mentioned Shaspa. So it's time to hear from the founder of Ethereum himself. I'd like to welcome Vitalik Buterin to the stage to talk about updates and future plans for Ethereum.
Today I'm going to talk about a topic which is kind of slightly off the path in terms of Ethereum's development with scalability and proof of stake and so forth, which is one very important consideration when designing any kind of blockchain protocol, which is basically when we're making a blockchain protocol, like we always talk about decentralization. And we always think of decentralization as this kind of very important thing that has to be maintained, that's very important. And are basically the reason why platforms like Ethereum are supposed to be, at least in some cases, better alternatives to running everything on a single central server, when the single central server can do 80,000 transactions a second and Ethereum can do 15. So, when we think about decentralization, we can think about how exactly will the level of decentralization of the Ethereum protocol change as a result of switching from proof of work to proof of stake. How will it change as a result of integrated sharding? And how are there any kind of changes to the protocol that we can make, that any kind of simple tweaks that we can make right now to reduce the risk that some kind of centralization issue will become a serious problem down the line. So decentralization is definitely by far not the only important property of blockchain protocols. And as I'm going to talk about in this presentation, I think of decentralization more as a kind of a means to an end, as a way of achieving several kinds of desired properties, than it is something that you want to kind of achieve as an end in itself. But the properties that we're trying to achieve are still very important, right? So, first of all, types of decentralization. So, if you look up centralized and decentralized distributed on Google Images, you get this graph, right? So on the left you have centralized, where you have one thing in the middle. In the middle you have, quote, decentralized, which seems to be a bunch of hubs with a couple of nodes at the edges. And on the right you have a distributed, which is supposed to be even more decentralized than decentralized, with no hubs. So, everyone remember this picture? Here's another person's attempt at explaining the difference between being decentralized and being distributed. Notice that it looks very, very similar to the first picture, except in the second person thinks that the word decentralized means what the first person thinks is distributed, and the second person thinks is distributed what the first person thinks is decentralized. So, my point in showing these pictures is that a lot of people have kind of very confused ideas of what even the word decentralization means, what the word distribution means, like what are the different qualities that we're trying to kind of jumble together here. So here's my kind of classification for different kinds of decentralization. I wrote this in an article on Medium about 1.5 years ago, where I try not to kind of make distinctions between the word decentralized and distributed, because if people can't even agree on what the difference is, we might as well just treat them as synonyms. And I try to talk kind of more directly about types of decentralization, where the three of them basically are, first of all, architectural decentralization, which basically means how many physical computers is a system made up of. So, and how many of these computers can it tolerate breaking down at any single point in time, right? So, is the system kind of architecturally fault tolerant? And if we want examples of things that are architecturally decentralized, blockchains, languages, protocols like Buterin, arguably common law as a legal system, and there's plenty of things that are architecturally decentralized as well. We can also talk about political decentralization, right? And political decentralization is not about the hardware, it's about who controls it. So how many organizations, how many individuals ultimately control the different parts of the system. And you absolutely can have systems that are architecturally decentralized but still politically centralized. So how many people here have heard of Cloudflare? Okay. So by the way, do people in the back here? Okay. How many people here think that agree that Cloudflare is architecturally decentralized? It has a lot of servers around the world, right? How many people here think Cloudflare is politically decentralized? It's not, it's a company. So the third important thing is kind of logical decentralization. And this is the one that's sort of hardest to define because it's more about, it's not about how the thing is built, it's more about how the thing behaves. So does the kind of interface, the data structures, does the functionality of the system look like it's a single object that you're interacting with? Or is it like some kind of amorphous swarm, like a cloud, right? So if you look at, for example, languages. Languages are architecturally decentralized. If you split the world in half, then people on one half of the world can keep speaking to each other, people on the other half of the world can keep speaking to each other. Blockchains are architecturally centralized, or sorry, logically centralized. There is one single kind of Merkle root, even inside of every single block. There's one blockchain, there's one history, there's one truth. And so blockchains are architecturally decentralized, politically decentralized, but logically they're very much centralized. And it turns out that I actually think this combination is very valuable. So, next question. Why do we care about decentralization? So I would argue that we have kind of three major reasons to care. One of them is fault tolerance. So basically, decentralized systems are less likely to accidentally fail because decentralized systems rely on many different components that are not likely to fail at the same time. Right? So that's one reason why you might want decentralization. So this is called redundancy. There's plenty of systems that are redundant already. A second one is attack resistance. Now, people talk about censorship resistance a lot, and censorship resistance is important, but censorship is really just one kind of attack, right? We want to be resistant against all attacks, regardless of whether they're called censorship, they're called hacks, or they're called something else. So decentralized systems are more expensive to attack, more expensive to destroy, more expensive to manipulate because they lack kind of sensitive central points that can be attacked very cheaply. Now, then there's also a third reason why we care about decentralization, which is what I call collusion resistance. So in a decentralized system, it's much harder for all of the participants in the system to collude, to kind of to cooperate in some way which is good for themselves, but which is bad for the system's users, which is bad for the other participants in the system, right? If you have a market where the buyers are decentralized, the sellers are decentralized, this is a perfectly competitive market, and there's plenty of economic theorems that say this works very well. If all of the sellers start colluding, and they all start agreeing with each other on what their price is, then this is called a cartel. And cartels are generally considered to be bad. So collusion resistance is also one other kind of important consideration that we care about. Now in blockchains, what is fault tolerance? Right? Well, we don't want the blockchain to just be able to shut down if say, one mining pool goes down, right? So, in the case of the Bitcoin blockchain, for example, there was an earthquake in Sichuan, I think, about a month ago, and this led to about 20% of the Bitcoin network's hash power temporarily going offline, right? So, how much disruption did that cost to the Bitcoin network? A little, but not nearly as much as it would have if Bitcoin was a fully centralized system. Attack resistance. So if there was one mining pool, then that's one mining pool that can be attacked, one mining pool that can be shut down. And collusion resistance basically means 51% attacks, right? So 51, in blockchain, generally 51% of the participants can kind of collude, and they can revert transactions, they can do all sorts of bad things. So, first of all, alternatives to decentralization, right? Decentralization is hard. Can we go without it? For those who can't quite see this, this is the UK's most secure data center, a nuclear bunker. If you want to achieve high reliability without decentralizing, you can try to do this. Cloudflare. So another alternative is that you can have architectural decentralization without political decentralization. So you can try to have partial decentralization. Service level agreements. So you can use reputations, legal contracts, incentives to basically encourage specific parties to make sure that they have very high availability. So basically, instead of trying to get reliability for the system by breaking the system up into many components, we keep the system as one component, but we just encourage that one component to behave very, very well. So these are alternatives, right? Another important alternative is that we can use game theory, right? So for collusion resistance, look, you can make a system more decentralized to make collusion harder, but you can also change the rules of the system in order to make collusion less effective. So even if there's 10 people at the table who make decisions, you can change the rules so that there is no opportunity for 6 of those 10 people to, say, come together and increase the revenues at the expense of the other 4. Now, in Bitcoin, the collusion resistance is not very high, right? If one mining pool has more than 23% of the hash power, then there's an attack called selfish mining, and that mining pool can start earning profits at everyone else's expense. And multiple mining pools that have more than 23% of the network hash power together can do the same thing. So we can try to build protocols that have better rules to them so that they don't have these kinds of issues. And this can solve a lot of our problems, even if there's still 10 pools in the entire network. So in summary, as alternatives to decentralization, we can make individual parts of the system stronger, we can try for architectural decentralization, we can incentivize availability, and we can use game theory to make collusion less attractive. So, attack resistance and Casper, right? So, first of all, Dewey wants to try to take the approach of making individual kind of centralized components much stronger and more resistant. And I personally would argue the answer should very explicitly be no, right? Basically, you definitely can create a system where instead of having a blockchain, you just have one data center, and this one data center is in a nuclear bunker, or you could even have 15 of them. But one of the main problem with this approach is that it basically, in practice, if there is a small number of nodes, then even if it's resistance to attacks, collusion becomes much easier. Right? There's certain other blockchains where there is a very small number of nodes that are controlling the entire network, and these nodes can just basically get on a call with each other and change the system's rules before they even tell everyone else that this is happening. So we do not want this to be possible, right? So incentivizing availability. So in Casper, in the proof of stake algorithm that we're working on, basically a node must be online at least 2/3 of the time in order to make a net profit. So what does this mean? Basically, it's an incentive for, first of all, for nodes to be online more if they already have signed up. But second, it's an incentive for participants that can't guarantee that they will be online for the most of the time to just not sign up in the first place, right? So, game theory. So there's actually been, as anyone who has followed myself or Vlad knows, there's actually a lot of game theory and mechanism design work going into the proof of stake protocols, right? There's some lose-lose games, fork choice rules, different blockchain designs, 51% attack mitigations. On the 51% attack mitigation front, one major kind of technology that's very important is client-side validation. So basically what client-side validation means is that individual users of a network are not blindly trusting what the majority of the miners or what the majority of the validators say, right? So even in the Ethereum blockchain today, if all of the validators collude, and all of the validators start pushing invalid blocks, and in these invalid blocks, they give themselves 50 million Ether for free. These are invalid blocks. And other nodes in the network will just verify the blocks for themselves, and they'll know those blocks are invalid, and they'll reject them. So 51% of the nodes, even colluding together, they can revert transactions, but they cannot cause invalid transactions to be accepted by the network, right? So this is one kind of very important kind of anti-collusion technology that exists, even in kind of decentralized blockchains, even in systems like Bitcoin and Ethereum today. And there are ways of extending these kind of client-side validation techniques to a context where there is a much larger amount of data that needs to be verified. And this is what things like fraud proofs and data availability proofs are for. You can also potentially even mitigate participants' ability to revert history. And that's what things like coordination gadgets and minority software are for. So, lose-lose games. So this is one very important kind of game theoretic primitive. So the idea here is that your reward depends not only on whether or not you personally participate, but it also depends on how many other participants participate in the consensus. So what this means is that, I should say offline instead of online, but what that means is that pushing other validators offline lowers your own revenue, right? So in proof of work, this is not true, right? In proof of work, the reason why selfish mining works is that if you have more than 23% of the hash power, you can perform this really clever strategy in such a way that you can reduce the number of blocks you create, but then you reduce the number of blocks other people create even more. And because Bitcoin, or proof of work has this difficulty adjustment mechanism, so altogether, everyone, like in total, everyone always makes the same amount of revenue. After the difficulty rebalances, basically, because you've hurt yourself less than you've hurt everyone else, you're actually, after the rebalance, you're actually benefiting. Whereas in proof of stake, this does not need to be true, right? And you can actually penalize everyone if some portion of the participants are offline. So there's many different kinds of lose-lose games, and Casper, and this is a fairly kind of important anti-harmful collusion mechanism. 51% attack recovery. So the idea here basically is, suppose that 51% of the participants do collude, and they collude in a way where they basically just stop accepting everyone else's transactions. They basically try to kind of capture the blockchain for themselves, right? So the way to solve this is basically through this kind of minority software, where the minority of honest participants and the users that see that this attack is going on can kind of come together, and they can basically create this minority fork, so they can ignore this part of the blockchain that's refusing everyone else's transactions, and they can basically continue on by themselves. Now, the problem with this kind of minority fork strategy is how do you actually coordinate? So how does a user actually know whether or not an attack is serious enough to be worth doing a fork over? And how do you make sure that two different users have the same opinion? So fortunately, Leslie Lamport invented an algorithm from 1982, which we actually can repurpose to kind of help us very significantly in this regard. So, incentivizing decentralization, right? So the techniques that I talked about so far are useful for, like, they actually don't increase decentralization by itself. And this is important, right? Because decentralization is not the final goal. Decentralization is a means to achieve the end. And so sometimes there are actually ways to achieve our desired properties directly. And our desired properties basically are the kind of reliability of the system without increasing decentralization itself. And Casper does a lot of that too. But we can also incentivize decentralization. So there's two ways that we can do this. One of them is this kind of fairly novel strategy that I call decorrelation incentives. And the decorrelation incentive basically means that, like in general, in Casper, if your node behaves incorrectly, then your node's deposit gets penalized, but the penalties are much higher if your node fails at the same time as other nodes. So this has two functions. First of all, it discourages people from kind of pooling all of their resources together and making these very large stake pools, because that can create centralization. And the second is it discourages shared infrastructure. So for example, it discourages everyone being on AWS. So let's say, for example, you already know that 30% of the network is going to be on AWS, and say another 5% of the network is going to be on some Google Cloud. What are you going to choose? Are you going to choose AWS or are you going to choose Google Cloud? Well, here's how you might think. If you go on AWS, there's some chance that AWS will get hacked. But if AWS gets hacked, then all of these other nodes will also fail. And so if AWS gets hacked, your penalty will be proportional to 30%. But if Google Cloud gets hacked, because only 5% of other people are on Google Cloud, the number of other people that will fail along with you is much smaller, and so your penalty will be proportional to 5%. So this basically makes Google Cloud much safer. It makes using anything that everyone else is not already using much safer. So this is what we mean by decorrelation incentives. The other important piece here is fixed cost reduction, right? So fixed cost reduction basically means, can we maximally reduce the fixed costs, so the cost that every node has to pay, regardless of how big or small they are. Because like in general, right, in any industry, if fixed costs are low, you can have high decentralization, but if fixed costs are high, then generally centralization and monopolies tends to be pretty inevitable. So quadratic leak is one example of a decorrelation incentive. Basically, penalty for you as a validator going offline tends to be very small. But if you go offline at the same time as more than 1/3 of other validators go offline, then your penalties suddenly start to be much larger. And also partial slashing. So basically, you can see from this kind of game theory diagram that if two participants get penalized at the same time, then they lose almost twice as much as either participant would lose, or as the participants would lose if you were to fail separately. So now, fixed cost reduction. Interestingly enough, sharding actually potentially increases the protocol's decentralization. And sharding is possibly the only kind of layer 1 scalability strategy that increases decentralization due to fixed cost reduction. And the reason basically is that if you just increase the block size and force everyone to process extremely large blocks, then the fixed cost, even for very small validators, will be very high. But here what we have is a system where the larger your deposits are, the more transactions you'll be responsible for processing, and the more data you'll be responsible for validating. And so the hardware burden actually kind of goes up in proportion to the deposit size, at least up until some point. So this basically decreases the kind of de facto fixed cost of operating a node very, very significantly by instead making it a variable cost. So areas of concern, right? So even the current protocol is definitely not perfect. So one of them is fixed costs in researching and implementing custom proposer strategies. So what is a custom proposer strategy? One of them could be accepting gas payment to different tokens. One of them could be making pre-commitments to include transactions at some future time. So a validator could make a kind of side agreement with some particular user, basically say to the user, hey, I'm going to guarantee that I will include your transaction in the next block. Another example would be fixed costs of researching and implementing custom deposit dual-use strategies. So validators have a deposit, but they can basically use that deposit as for multiple purposes at the same time. One part for Casper, one part to also guarantee that they'll behave well in kind of other mechanisms at the same time. And there are probably high fixed costs in kind of researching and implementing these strategies. A third one is also fixed costs in staying online 24/7. So how can can we mitigate them, right? One important strategy is to try to move things to kind of layer 1.5, right? So what we mean here is basically that if somebody wants to pay for gas in, say, I don't know, Ethereum Doge tokens, because that's now a thing, then you don't want to require actual proof of stake validators and block proposers to accept Ethereum Doge tokens. Instead, you have an intermediary layer. And the intermediary layer accepts Doge tokens and basically packages up transactions and puts them on the blockchain. And the intermediary layer is responsible for making transaction fees in Ether, right? And so the intermediary layer basically helps you exchange the Ethereum Doge tokens for the Ether. And the point is that basically instead of trying to have this full economic abstraction at layer 1, because that would actually put a very significant burden on kind of validators in researching all these strategies, instead we encourage the development of these kind of intermediate layers that can help solve these problems. Don't encourage stupid race condition gaps. So there's a lot of ICOs that have happened over the last year, and a lot of the time these ICOs have these really kind of crazy mechanics where they do things like they say, oh, the first 100 participants to get in can get in at some very high, at some very favorable rate, and everyone else kind of gets kicked out. The problem with these approaches is that basically, if you think about it, who decides who are the first 100 participants that get in? It's basically the miners. And so the more dApps like this exist, the more incentive there is for miners to spend a lot of time on researching strategies on basically how to exploit all of these games as much as possible. And the more of these games exist, then the more this basically ends up encouraging centralization because, well, how many people around the world actually know how to best implement these strategies for miners to extract all of this revenue? Fixed costs and staying online, well, we can reduce that with decorrelation incentives. We can also try to make the blockchain lighter, so we can do things like staking off your phone instead of staking off a laptop. So there's lots of ways of doing this, right? So, for conclusions, I guess a very important goal of a blockchain is to kind of balance between these two goals, where one of those goals is scalability, performance, low latency, all kind of usability properties, and on the other hand, decentralization. And there definitely does need to be this kind of large focus on not just decentralization itself, but also reliability, fault tolerance, attack resistance, collusion resistance, all these properties that really are the reason why we are trying to build decentralized things in the first place, right? So you can target decentralization explicitly, but you can also kind of more directly target these other goals. So we can target those other goals. If we want to target decentralization explicitly, then we can use decorrelation incentives, and decorrelation incentives can encourage both kind of political but also architectural resistance. And we can do, and decorrelation incentives have this nice property that basically, if you penalize people more for failing at the same time as everyone else fails, then you are basically incentivizing people to make their infrastructure kind of robust relative to the rest of the network in the right way. And what this also achieves is it basically allows us to do this while at the same time keeping the mechanism relatively friendly for most users in the normal case. And another important thing that we can do is we can reduce fixed costs, right? So these are kind of some examples of the design considerations involved in, and we kind of go into, when we go into proof of stake and shorting, how do we prevent, or how do we kind of maximally limit the possibility that various kinds of centralization risks will show themselves? Do I think we'll be 100% successful? No, because if I thought we'd be 100% successful, I would have just had one strategy to rule them all, right? Here I talked about optimizing decentralization, optimizing collusion resistance under centralization, reducing the effect or increasing rogue resistance against 51% attacks. So I think in the long run, 51% attacks may well happen, and we need to be able to handle them. But ultimately, these kinds of defense in depth strategies are probably the most reliable way to kind of build blockchains that can last several decades or longer going into the long term. Thank you.